Yep. Hello, everyone. Welcome. Thanks for coming. It's great to see so many people in the room, and I believe we've got quite a few people joining us online as well. This is the first of a number of seminars through the Southwest Nuclear Hub, kicking off our new CREST Award. So congratulations to everyone involved in that. Well done. That means something to people in the Faculty of Science and Engineering at the University of Bristol, and anyone who isn't in that faculty will discuss that another time. So today we're here with Professor Tom Scott, who's the Director of Research for the Southwest Nuclear Hub, to talk about Chernobyl 40 years on. So it's been 40 years since the Chernobyl disaster. And whilst that day in March 1986 was very significant in nuclear in the world, it isn't the totality of the Chernobyl story. And so Tom's going to give us a picture about all the work that he's been doing over the last period of time. Probably not 40 years, but yes. So please join me in welcoming Professor Tom Scott.
Thank you very much, Tom. And thank you very much, everyone, for coming. It's lovely to be in a lecture theatre where I pretty much know everybody, and that makes it more fun to talk about all of this kind of stuff with you. So, of course, Chernobyl is, I think, for most people in the public, synonymous with what happens when nuclear goes wrong. And it's also a sort of focal point for people to look at and to comment on as to why we need to be careful about doing nuclear in the future as well. Of course, hindsight is always 2020. For what happened in Chernobyl, that's certainly the case, whether you've seen the HBO mini-series on Chernobyl, or you've come to lecture courses in the School of Physics. Chernobyl is a great example of human error, which is partly through human error in design of a reactor, but it's also human error in terms of a lot of what went wrong with the Chernobyl disaster. They were doing a safety test where people went off-piste in terms of what they were supposed to be doing. Following standard operating procedures is really important in the nuclear sector and industry in general. And if you go far off those standard operating procedures, then things can go really wrong. What I would reflect on about the Chernobyl disaster, and it was a disaster, was that those people in the control room at the time, they genuinely thought that with everything going out of control, they had one fallback option that made everything safe again, and that was to hit the red scram button. And I've been really, really fortunate in terms of what I've done to support Ukraine, to support Chernobyl. I've been able to stand in that control room. I have stood at the panel, and I've stood with my hand over where that scram button existed. It's not actually there. They've removed it now because it got contaminated. But there was that sense from being there and being in that location that something significant had happened there. But it was also the sense that struck me is genuinely they thought by pressing that button, everything would go and stop. In fact, it didn't because of the design fault in the reactor. It actually caused the explosion to press that button. And then everything after that, to some extent, is history. Now, of course, the destruction of reactor unit 4, pressing that big red button, essentially caused an explosion which threw the graphite reactor core up in the air to land on its side, and to then subsequently set fire to the graphite. So essentially a very horrendous nuclear barbecue was started, which spread radioactive material over large parts of what is now Ukraine, Belarus, but also spread radioactive material as far as North Wales in the UK, large parts of Scandinavia. And that contamination was very, very detectable. And that caused, for example, in the UK, for those affected parts of land, you couldn't sell produce from that land up until actually about 10 years ago. So significant long-term effect. And of course, there was an immediate response to that. You had a fire situation, it needed to be put out. And as part of that, they also evacuated a large number of people. So the town of Pripyat, which is the closest to the Chernobyl reactor plant, was evacuated. That was about 50,000 people that were moved very, very quickly. But the whole exclusion zone which is it's about 1,000 square miles of land was evacuated. So that's a really large area, of course. And of course, today, the exclusion zone still exists. It is still an exclusion zone. So the picture you can see, the black and white picture, these are what are called bio-robots at the time, as coined by the Soviet government. And human beings were used to do a lot of the cleanup. And we're talking more than 100,000 people, mainly soldiers, brought in to actually do the cleanup. And of course, a big mess. So part of solving the problem in the immediate aftermath was you had to put the fire out. That was achieved mainly by chucking sand with boron in it, as well as lead shot on top of the reactor building. And that required people in helicopters to fly over the top, essentially with these big bags of sand and gravel, and to drop it in. If you've seen the miniseries, there's a bit where the helicopter crashes. Okay, the helicopter does not crash because of the radioactivity. The helicopter crashed in real life because its tail rotor hit a wire that was hanging from one of the cranes, and that took out the tail rotor and caused the helicopter to crash. So radiation didn't cause the helicopter to crash, but helicopters needed to fly directly over the reactor core in order to put the fire out. But nonetheless, putting the fire out was the biggest, most important thing to do. Once the fire was out, you still had a reactor core, which was essentially open to the elements. And that's not a great thing with regards to wind and rain and further spread of material. So what happened really, actually, from an engineering perspective, really very quickly, is they built the sarcophagus, which was designed as an emergency structure. And they actually prefabbed concrete sections. They called them hockey sticks. And they made a structure very, very quickly using cranes, where they piled them on top of each other and stacked them up just like you would with a child with bricks. You balance them on top of each other, and just gravity is holding the structure together. And that was the only way to do it, because you couldn't have people near to the reactor because there was too much radiation. It was too intense to allow human beings really, really close to that core. And so this stacked structure was created really quickly. Now, of course, because the structure was stacked and because it was made really, really quickly, it wasn't designed to last for a long time. And so within 10 years, they started to see that structure degrade, started to crack, bits started to fall off it. There started to be holes where the gamma could shine out and be quite dangerous. And so by 1997, so within approximately 10 years, the international community, which was mainly the European Union funding this, had put a big amount of money towards building a more permanent structure, which could envelop the entire Unit 4 and sarcophagus to essentially seal it up. But inside is still the problem. Inside the sarcophagus is still the problem, where you have fuel, which is melted, and some of it has, as a sort of molten radioactive lava, has escaped into the basement, which is never a good thing to happen with radioactive fuel materials. But there's also debris all over the place. It's not structurally sound. And periodically, actually, you do get partial miniature collapses within the structure, which can cause releases of material as aerosols, which isn't good. So the hazard, which is still represented by that breached reactor core, still exists today. No one has done anything substantial to intervene with it. All that's happened so far is that structure has been better contained. And what I would say, in the 40 years since the Chernobyl disaster has happened, one of the engineering positives behind this is that history has been made. The largest movable engineering structure ever made was built about 100 meters away from the reactor core. It's called the New Safe Confinement Structure. It cost about 2.1 billion euros. And the point of that structure is to form a hermetic seal over the top of the sarcophagus, such that if Unit 4 materials do collapse, or if the sarcophagus falls apart, then to some extent the concept was that's okay because we've got this superstructure which envelops it and keeps it hermetically sealed from the outside world. Now, to put into context just how big this arch structure is, the Wills Memorial Building I was looking at, so which is the big cathedral-like building just at the top of Park Street, that's 63 meters high. Okay, the height of the arch is 108 meters. So you could do approximately 1.5 Wills Memorial buildings before you're touching the top of the roof. This is an astoundingly large structure. And what's more astounding is it's a movable structure. So they built this structure 100 meters away approximately, and then moved it into place over the top of the reactor core. And the reason they did that? Quite simply because there's too much radioactivity, even with the sarcophagus over the top, there's too much radioactivity shining straight up out of the reactor core that you could ever conceive of putting people over the top of the reactor. It's just too dangerous. So the point about everything that was done up to July 2019 was about containing a problem, which were actually, if it was left undisturbed, was only going to get worse. And of course, July 2019 was just before we hit COVID, if you remember. So this amazing structure is built, it's ready to go into operations, then effectively, because COVID strikes, nothing really much happens inside. What was originally planned is that they would build this structure, put it in place, and then they would start dismantling and deconstruction of the sarcophagus and then Unit 4 inside. But actually, nothing really up to this day significant has happened inside because of, first of all, COVID, second, Russian invasion of Ukraine. Okay, but the concept that they developed crudely for doing this is within the arch structure, you have some absolutely huge gantry cranes. And on those gantry cranes, they have some suspended platforms, which you can put robot arms onto. And those robot arms would be lowered in over the top of the reactor core and would literally lift off block by block, concrete chunk by concrete chunk, and disassemble the reactor and put each block or each chunk into a suitable storage vessel. So if you think about a sort of playground, or if you go to the seafront at Weymouth, you have those machines where you have the grab and it grabs the teddy bear or whatever you're trying to grab. That's where you usually lose your money, isn't it? But that's more or less the concept that they are going after for deconstructing the sarcophagus in Unit 4. And that's all got to be based on using robots, not humans. Humans cannot go over the top of the reactor, and humans definitely don't want to come into contact with the radioactive debris materials. So it's a very, very challenging environment. I think you'll agree. This is a photo which is looking up from one of the gantries down towards the reactor. We can see there's some scaffolding up the front, and there's essentially a metal plate that's stuck onto the front of the face of Unit 4, which is there to stop it from falling down for the most part. It does provide a bit of radiation shielding at the same time. And you can see this big yellow structure across the top. This is one of the gantries, which is movable all the way up and down the whole length of the new safe confinement. So in terms of thinking of this as a engineering challenge for how you deconstruct a nuclear reactor, which is in a terrible state of repair, let's say, you've got the problem that you're working in a confined space. You've got very unstable structures such that there's a good possibility when they try to move some material, that other material that's in the immediate contact with it might collapse and release radioactive aerosols. And that means that in terms of humans being allowed in while any operations are going on, humans are not allowed in. Okay, the only times you can go into the new safe confinement area around the reactor is when there's nothing happening and the levels of aerosols in the air are measurably sufficiently low that you can go in wearing full protective equipment. And we've done that. My team's done that. So the other thing is that the radiation levels do vary. And as you would take apart a reactor, you can imagine the radiation levels will change, because sometimes you're lifting out spent fuel, sometimes you're lifting out spent irradiated reactor graphite. And ideally, over a function of probably what would be 20 years of dismantling that's still ahead of us, those radiation levels should decrease as you start to move material out. But in the interim, it's quite likely that radiation levels will spike in order to get to the ultimate objective, which is complete dismantling of the plant. So it's really hazardous for humans. It's really challenging to do this with robots as well. So robots are not invulnerable to very high levels of radiation, but they're a lot more tolerant. So robots really are part of the solution, with humans at a safe distance, either remotely controlling or remotely supervising, but that's the way that this is going to be done. It's not been done yet. So robotics is definitely a key part of the solution, and that's what my group here in the School of Physics have been working on for, well, since the Fukushima disaster, actually, different robotic technologies to help in the aftermath of nuclear incidents. And that means it's robots where we can deploy them remotely, whether that's us 100 meters away or kilometers away. That's a challenge in itself. When you're working at distance from the robot, what you need to actually do is try to get the robot to do more for itself. And that's where we have done a lot of work on increasing autonomy of these systems. So, for example, with the work that we do with UAVs, a lot of the time, the UAV is flying itself in a predefined pattern, but the drone is flying itself, and the human pilot, which is people like you in the audience, they are supervising in case the robot decides it's going to do something wrong, at which point the pilot takes over very, very quickly. But it's most efficient often when the robot's doing the work autonomously and it's supervised. We also do a lot of work around mapping radiation, because radiation is risk. And if you understand where the radiation is coming from, you understand how strong it is, you can qualify that to risk to people. And you can set up, for example, zones where people shouldn't go, or you can define zones where it's okay to go because it's safe enough. And that's really, really important when not only you're working at Chernobyl, but some of the surrounding plants and storage facilities where the levels of radiation are very changeable and sometimes unpredictable as well. So this idea that robots have to be a key part of the solution because it's not safe for humans. Humans, in my opinion, are not expendable. But of course, that wasn't always the view. So the idea of robots in nuclear emergency response and cleanup is definitely not new. In fact, they tried it in the immediate aftermath of the Chernobyl disaster. So I'm going to draw your attention to the really big picture and ask you to see if you can see where the robot is. It's a bit like Where's Wally? I'll give you a clue. The robot's yellow. Yeah. So that is the Joker robot. And Joker was one of the first robots to be deployed in the aftermath of Chernobyl. It was a German-designed robot, West Germany, which was originally designed to be doing routine tasks on nuclear sites. But then with it being in West Germany, it had then been adopted for use in bomb disposal, so CBRN type applications. So after the Chernobyl disaster happened, one of the first things was Joker was called in. The people that operated Joker knew very well how best to deploy their robot, but they were overruled by the authorities at the time, and the authorities at the time said, we're going to airlift it directly onto the roof, exactly to where it pretty much sits now. And what happened is, as soon as it got airlifted onto the roof, and you can see that there's a cable coming out the back of it, the first thing it did is because it didn't have a run-in to get to the roof, when they started it up and moved it forwards, the first thing that happened is a big chunk of irradiated graphite got stuck in the track. And the irradiated graphite was so radioactive that it fried the electronics within about 10 minutes, which killed the robot. And actually, that had quite big implications because the robot had died, and the joke was that the robot was a joke. That's how the Soviets talked about it. So they had to then decide that there was not a robot solution they could immediately use, and they went to bio-robots, which I think was the least desirable thing, but it was the only immediate thing they could go to, and that was 3,000 Soviet troops. They were given an option. You can either deploy to Chernobyl to assist with the cleanup, or we deploy you to Afghanistan for the next 10 years. Difficult choice, right? But so at least 3,000 of them said we'll do the nuclear job, and so they were deployed to the site. They were wearing homemade protective clothing to try and shield some of the radiation. So that was essentially bits of lead or steel shielding as armor that they were wearing on top of boiler suits. And depending on exactly where they were working, they were limited to anything between 30 seconds per shift to 10 minutes per shift. And that's simply because the levels of radiation were so high, that's as much time as you could afford before it was likely the radiation was actually going to cause you some immediate harm. So that's pretty scary as a thought. I think you'll agree. And what these people were doing is they were literally, with their protective suits on, were running out onto the roof of the reactor and taking a shovel full of material, running to the edge of the building and throwing it back into the gaping maw of Unit 4 that was still open. Incredibly brave, but at the same time, I would say incredibly uninformed as to probably the level of risk that they were being exposed to. So this is the inspiration for why I do a lot of my work. So this is Joker, and I'm just going to show a little short video, because Joker is sitting exactly here today, and he's sitting in what is called the vehicle graveyard. I filmed this 5 years ago, obviously. Now, 35 years on, we have our own yellow robot. If anything like Joker, in fact, instead of rolling onto the site, it's going to walk onto the site. So one yellow robot meets another yellow robot 40 years on, approximately 35 years on. And the juxtaposition of these two yellow robots, I think, is quite significant, because you've got the Joker, which didn't last too long. And if it had been deployed properly, would have actually probably done a lot better. And then you've got the Boston Dynamics Spot robot, which is actually now quite famous. And we were the first group in the world to ever deploy Spot at a nuclear site, and that was Chernobyl. Since then, we now see Spot used at nuclear sites on a daily basis all over the world. And part of that was us showing on the worst nuclear site in the world what's possible with this kind of technology. So just to compare then and now, if you like. So the robots that were originally tried and tested in the aftermath of Chernobyl, we've covered Joker already, but there are a couple of others. I think for me, the most interesting one is the Moonwalker Soviet robot, which I've also met in person, was actually designed to be a moon lander for the Russians. It was a moon buggy, essentially, that they modified to turn it into a robot. But the chassis is a thing of engineering beauty in terms of it's made of titanium, the wheels are titanium, and the tread on the wheels is welded titanium strips. It's very, very cool, and it's coloured white, as if I think all moonlanders need to be white, maybe. But again, it was an example where they tried to use technology that was available at the time and to reappropriate it for the use in the aftermath of Chernobyl. I think what's most important is all of that technology was analog at the time. And of course, we've since over the last 35, 40 years, we've got now amazing digital technologies and microelectronics. And intrinsically, because hardware and computer chips have got much, much smaller, that has made it much, much radiation harder, if you like. So modern microelectronics can withstand much more radiation than the equivalent analog components at the time. And because we've, in terms of software engineering, got a lot further, those robots that we have now can do much more by comparison. So modern capabilities are things that I've deployed in the Chernobyl exclusion zone and plant are things like winged UAVs, where you can fly and cover many square kilometers in a single flight. Multi-rotor UAVs, which we can use to fly low and slow over particular areas of interest and get really high resolution data. And the Spot robot as well. And you can see the Spot in that picture has an arm on top, which can open doors to let itself in. And it can also be used to do things like take samples as well. And also some of the tech that we've developed, which would still count as sort of robotics, is handheld robotic tech as well. So sometimes there are places that you can go if you're quick to get data where it's more efficient because of complexities of that environment. It's more efficient to send a human in protective gear to do something very quickly than it is to send a robot that's more likely to get stuck or hit into problems. So our story in terms of the Bristol work at Chernobyl actually starts back in the aftermath of Fukushima. The University of Bristol's had a long-term collaboration with the University of Kyoto. We're sort of partnered universities. And in the aftermath of Fukushima, which actually March 2011, we started developing technology with Kyoto, with the Japanese Atomic Energy Authority, and we developed radiation mapping drone technology, which we subsequently deployed very extensively around the exclusion zone around the Fukushima plant. And because of the work that we'd done there and because of its success, because of the impact we'd had, that got us an invite in 2018 from Chernobyl nuclear power plant and the Chernobyl exclusion zone to come and deploy the same technology there in order to assist with the cleanup of not only the power plant, but the exclusion zone around it. So our first sort of serious deployment of technology was in 2019, where we mapped 22 square kilometers of the exclusion zone. But we focused on the infamous red forest, which I'll come to later. But we also then, 2020 and 2021, were deploying the Spot robot inside the new safe confinement structure, in the control room, on the pile cap of Unit 3, in places that were really quite interesting. Unfortunately, our work in Ukraine physically, in terms of us going there, stopped. Our last visit was September, October 2021, and in February 2022 was the invasion. So we've quite logically not been back there since, but we have continued the collaboration and we continue to support, and I'll explain that as well. But if you look at this sort of edifice, and this is one of my team taking a photo of the edifice on the front of Unit 4, it is an absolutely huge structure held within an even bigger structure. But the thing that you pick up is it feels quite like being in a cathedral or a church. It has that echo. It has that silence of people aren't talking. And so it feels actually like something really significant has gone on there. And it was one of the places which, in terms of deploying technology on the robot dog, etc., we could get some very, very good data. You can see this picture in the bottom with the green, with the red and yellow spots. That's actually the pile cap. That's the top of reactor Unit 3, which sits immediately next door behind a concrete wall to the stricken reactor core. They sit back to back. And this was actually done with one of our scanning units, and one of the PhD students at the time and myself, Matt Ryan Tucker. It took about 22 minutes to scan the whole of the pile cap for Unit 3. So really, really quick and really very precise on where radiation was coming from. And that's part of the trick, is recording data really precisely, really quickly, and being able to see it in real time. That's one of the biggest challenges that we've overcome. Now, with the red forest, it's called the red forest because when the explosion and the release of material happened, a significant amount of the fallout landed directly to the west of the power plant on a forested area, and the radiation levels were so high it killed the trees. And in killing the trees, they turned orange. So it should be called the orange forest, but the nearest translation that came to sort of persist was this was the red forest. So it's the most contaminated area of land for radioactivity in the world. And it's not safe for a human being to walk into the middle of the forest because the dose levels are too high. So the way to be able to map the red forest is to do it with UAVs, which we did with fixed wing and then multi-rotor drone systems. And the first time we attempted to do this map, we had no idea of the levels of radiation, and we saturated all of our detectors. The radiation levels were too high. We worked out we'd need to be at 320 meters to not saturate the detectors that we'd packed at the time. So very quickly, we brought the drones back, we took them back to the lab, we changed the detectors, and we were able to go back again and then map the whole area without saturating the detectors, and to provide the highest resolution maps of risk. Essentially, this is a risk map to show the areas where you shouldn't go and the areas where it's a lot safer for people to go. It also started a foundation. We were bringing really good drone tech to Ukraine. So when we were deploying this, we got an awful lot of Ukrainian government interest in the technology. Often that would involve us being taken by angry-looking special service guys into rooms to be asked about the drone, which we would have been very happy to do if we'd just been asked nicely, I think you could say. But this data became very, very important in April 2020, which is when a lot of us were in lockdown. Wildfires broke out across the Chernobyl exclusion zone. In fact, subsequently, they were able to prove that they were deliberately set. Arsonists set fire to the Chernobyl exclusion zone. There's lots of trees, it's very heavily forested. And the weather and wind conditions were such that the fire was being pushed towards the Red Forest. And the Ukrainian government, the UK government, the European Union, the American government all got very upset with the idea that if you set fire to a really highly radioactive forest, then there must be a radioactive release into the air. And so what's going to happen? So our data was incredibly important for underpinning the predictive modelling exercises which the different governments undertook to be able to predict whether the embassy in Kiev, for example, needed to be evacuated. So it was a great example where our mapping had become suddenly very, very important. So we were working with Langley, with NASA, for example, Ukrainian government with the Met Office in the UK to be able to show what was likely to happen if the fire propagated all the way right into the Red Forest. Now, luckily it rained. Just before it reached the really nastiest areas, it rained. But without that underpinning data, no one could have planned a suitable response. We also did a lot of mapping at sites around the nuclear power plant as well. There's lots of storage sites. If we've got time at the end, I can show you a really cool video of what's called the vehicle graveyard. But in the vehicle graveyard, literally when the liquidators finished with their cleanup, 100,000 people means an awful lot of equipment that was literally transported to what's called the graveyard, which is effectively a really big car park with razor wire fences, and it was just left there. And it was left there without any cover, without any protection. It's open to the elements. And of course, records over time are lost. And it came to the sort of situation where the Ukrainians are saying, well, we've got the vehicle graveyard, but actually we don't really know what's in it in terms of radiological threat. So could your robots help us understand where it is? So that was robots in the air and that was robots on the ground. And you could see Spot having a little sit down to have a rest. And the reason that he's doing that is because it's 3D laser scanning the tanks, 2 tankers that are immediately to the side of it. And it's recording the radiation coming off those tankers to work out which one actually is full up of radioactive material, sludge, and which one was emptied before it was brought there. And they genuinely didn't know that even any of the tankers held any residual radioactive materials. So this was an example where the drone told us first where to go, roughly, and then the robot dog was sent in to have a detailed look and to then specify the exact location of those emitters. So this is one of the fun things in terms of flying drones over the top of the vehicle graveyard. So you can see a picture of the drone, but then of course you should think, well, how did Tom take a picture of the drone in the air from above? And that's because there was another drone following the drone, which was really good fun because I was flying the one that was following the big one, which is much more fun than the boring bit, which is following the big one bit is a bit boring. But that led to a lot of work that we've been doing through PhDs like you and Woodbridge in terms of the raw data that you record. You can see in real time on maps like this, where we broadcast it locally to controllers on Apple devices. So you can see data in real time, you make decisions in real time. But then if you really want to pinpoint exactly where the radioactivity comes from and you want to understand exactly or more exactly the intensity of the radioactivity, then we do something called an inversion. So Ewan's PhD has been around based on inversion, which is algorithms that allow us to pinpoint the radioactivity and localize it so that you can go from understanding where the radioactivity is coming from within about 10 meters to within about 30 centimeters. And that's pretty specific. And that's really, really good for nuclear response scenarios, but it's also good for things involved in homeland security. Another thing that we did is we used the robot dog to look at tourist areas. So prior to the invasion of Ukraine, there was about 100,000 tourists per year going to the Chernobyl exclusion zone. And they'd sign up with tour companies that would take them into the exclusion zone. But there was very little control other than the controls on letting them into the zone as to where they would go. And there were, based on the work that we've been doing, based on the large area mapping, we'd found localized areas of very high radioactivity that the Ukrainians didn't know about. And it seemed that some of these areas were also coincident with where they were taking large numbers of tourists, which you would think is not a great mixture. And one of the things we identified as a problem is what we call fuel fleas. Now, these are tiny particles of spent nuclear fuel that were thrown out of the reactor during the explosion and the fire, which lie randomly distributed around the exclusion zone. And if you come into contact with a fuel flea, the radioactivity levels are very, very high. Just to give you an understanding of that, with the robot system, we found a fuel flea. It's about 1 millimeter in size. So think of it as being like a coarse grain of sand. In order to appropriately shield that so that it could be taken to the Ukrainian facility in Kyiv, it needed 65 kilograms of lead surrounding that one particle in order to shield the radiation enough such that you could move it. And it was moved in an armored personnel carrier, and I was following behind it in a Land Rover, which was really good, but also really slow, I have to say. So using the robot, using Spot, very much like a real dog, and this, this is sort of bio-inspired in terms of how a dog or a pig might sniff out for a truffle or something that smells really good. We were using the robot in exactly the same way. So we mount a radiation detector on a boom, and the dog can mimic how a real dog would sniff out for something good by forming an arc and moving the detector across an area in order to be able to, again, pinpoint. And you can see where this video stopped is right over the top of the source. And it's not doing it because it can see, but it's doing it because it's localized exactly where the radiation source is. So with all this kind of technology in hand, the most notorious deployment was at the Chornobyl power plant itself. So the first thing you see your structure, which is 108 meters high. It's pretty big. And the other thing to note is Spot's quite heavy. It takes 2 people to lift and carry. And in order to get into the reactor building, there's something called the Golden Corridor. It's about 1 kilometer long. So carrying a really heavy robot dog in full PPE for 1 kilometer, I think was something we hadn't trained for. I think Dave and Yannick would agree with me. That was not the most comfortable thing to have to do. But luckily there was enough of us that I didn't have to carry it all the way back. I delegated responsibility. One of the things we also had to do is we needed to, just like humans wearing PPE to cover our feet to stop contamination getting onto our shoes, we did the same thing with the dog. You can see just poly bags, but we also tried children's Veruca socks from swimming pools because they work quite well as well. But the point of using the dog is if you've got contamination on the floor, you've only got 4 points of contact with the ground, and they're relatively small points of contact. Where, for example, the Joker robot was a problem is it had tracks, and the tracks were scraping up radioactive material and depositing onto the robot itself. So if you want to use a robot for inspection and radiation mapping, you need to make sure it doesn't contaminate itself, because otherwise all of its brilliant sensors on board, all they do is measure itself. And that's not really useful or helpful. You can see that we were allowed in. We just weren't allowed near the reactor. We had to stay back more or less against the back wall. And the thing that you note when you go into that structure is the first thing is a blast door comes back and all of your dosimetry alarms go off and they say, just don't stay still, go left or right. And that's because they built, without knowing, they built the entrance to get into the sort of main atrium directly in front of the shine path coming out of the reactor core. Hindsight's a wonderful thing. If only they'd done radiation mapping first. But once you'd gone left or right, the radiation levels were safe enough, Christian, that it was okay. And of course, what we were doing there with the robot dog, we were using a collimated gamma spectrometer with a laser scanner to essentially scan the front of the reactor and to measure the shine path coming out of the reactor core and understand exactly where it was coming from, because it's not uniform. And it's certainly not uniform because of all the debris that's everywhere. So that was Spot. But that's really September, October 2021 was the last time we were physically there to do and deploy our technologies. And of course, because of the Russian invasion of Ukraine, we're not going to be going back there anytime soon. So the logical thing in order to continue to help the Ukrainians was actually for them to come to us in Bristol. And that was the Titan program funded by our government through the Department of Energy and Net Zero, but also through the Norwegian government through their nuclear safety regulator, the DSA, have funded us over the last 3 years to develop a bespoke training course for teaching nuclear operatives how to respond to nuclear emergencies, how to use the most modern and best robotic and sensory technologies to give them risk information really, really quickly. And so far, as part of that, we've delivered 4 specialist training courses, which is a combination of lectures delivered by our team, which includes some of the PhD students as well. It's hands-on training with robots. It's field exercises, which are as real as we can possibly make them. And it's all about giving them a greater resilience to respond to incidences. And there obviously have been incidences since the invasion where that kind of skill and capability has been very much needed. And this will be an activity that we will certainly carry on. It's also in terms of being able to deploy UK developed robots and sensors in someone else's country, in a nuclear exclusion zone, in the world's worst nuclear disaster location. You don't just do that on your own. You need a lot of collaboration. You need to have on board lots of people involved in, and there's a menagerie of lots of different Ukrainian government organizations to give you the permissions, to give you the accesses, to help you with the risk assessments, to be able to do these kind of deployments. So some notable people, Dr. Maxim Savelyev, who's been our biggest supporter, who actually works on the Chernobyl site, but he's a professor in physics at the institute that's attached to them. Margarita and Anastasia, who work for SWNH, who is one of the sort of more senior government organizations that could give us accesses in the first place. But also to my brilliant team, and Dave even gave up his birthday to be in the exclusion zone. It's probably the nastiest birthday cake anyone's going to ever eat. And I'm not sure Dave actually dared eat it, to be honest. It wasn't because the radioactivity, it's because the food is so disgusting in the exclusion zone. But very much all of the work that we've done has been done in very close partnership with the Ukrainians. And when you spend a lot of time together in these kind of special situations, you do form bonds and attachments. And so it's been really challenging for the team not being able to go out there and help our friends and to hear from them everything that they're going through. It's really, really tough. And that's why we're so committed to continuing what we've already started. And that's because we've only just started helping. There's at least another 40 years of work ahead. I'm not going to be doing this for another 40 years. I tell my family in the audience, but there's a number of really big things that we need to get to grips with. The first one being that ultimately we do need to take apart reactor unit 4 and take all of that radioactive material and put it somewhere safe. And ultimately that would be underground in a geological disposal facility, which doesn't exist yet. The plans for which don't exist yet. So there's an awful lot to do in terms of retrieving that. And that's going to be achieved with the robots, not humans, because the materials are so nasty. So that's going to need lots of things from digital twins, the ability to adapt your plans, whether that's guided by humans or it's decided autonomously. That will be really interesting to work out. It's novel types of sensor. So there's an awful lot of interesting science and engineering that we can participate in to help with this. A bigger ambition that I really want to get to grips with is shrinking the exclusion zone. So 2,600 square kilometers of land, but we can evidence that probably up to 50% of that has low enough radiation levels that it wouldn't be any different from what is background immediately outside the exclusion zone. And so we can shrink that land area and free up land as being clean and usable, then that can help Ukrainians in their recovery in terms of their economic activities, their output. So freeing up land, not for agriculture, but for industrial utilization, solar farms, wind farms, etc. That could be really, really useful for helping the Ukrainian country recover from the problems it's been dealing with. You've also got to deal with these interesting nuclear wastes, which aren't your standard nuclear fuels in nice containment, but it's blocks of molten corium that need to be lifted out and made safe. Incredibly high radioactivity, incredibly interesting challenge for robotics. And the last thing really is about translating technologies. What we've developed in Chernobyl, what we've been able to demonstrate, first deployments of UAVs, walking robots, it has opened a gateway for other sites, nuclear sites around the world to start using the same technology. So our impact, which is still growing today, has been enabled by what we've done at Chernobyl. And of course, in the Middle East at the moment, this is one focal point for our technologies that are suddenly getting very prominent and important. when nuclear facilities are being hit by ballistic missiles and drones, again, which we shouldn't be doing. But having that ability to respond with the right technologies is super, super important. So that's for the next 40 years. I'm going to look forward to a drink this afternoon. But I would like to acknowledge my amazing team. I'm going to ask all of my NTR and robotic team to just stand up, please, because this has been achieved. Come on, you and Liv. Come on, anyone involved with Titan? Come on, Alex. Super, super important to understand that it's not just me. This doesn't happen with just me. It happens because of a whole team. It happens with support from the School of Physics, from the exec to the safety team. It's an awful lot of planning and hard work from people to do things which really make a difference. So please let's give them a round of applause. And with that, thank you very much for your time. Any questions? Alex.
How much tolerance is this?
The people online need to hear.
So with respect to the lifetime of new safe deployment, how much tolerance is there for delays to?
Well, it's an interesting one. People might have read in the news that the new safe confinement was hit by a high explosive drone, and that punched a hole in the side about 15 meters wide and set fire to the interspace in the arch structure, and it caused quite a lot of damage. And of course, to put a fire out, you use lots of water, and with the structure, which is a double skin structure, is now filled with lots of water. So originally, the new safe confinement was designed to last for 100 years. It can no longer be technically underwritten to last beyond, I think it is about 2030, 2035, which is not very good. So what that means is if you can only guarantee that the new safe confinement is providing you good structural containment for a certain period of time, it really focuses the mind that you need to get on with the job of dismantling quickly. And, you know, you can't take 40 years to do all of it. You need to start addressing some of the really high risk stuff sooner rather than later. I say that also recognizing that they're still being invaded by the Russians. They're still being attacked on a daily basis as a country by the Russians. And that's a really tough challenge ahead. So as much as we can, we really want to help them. One of the things we've supported them in is mapping the radiation over the top of the arch. Almost immediately after the drone strike. The reason that needed to be done is someone needs to fix the hole. So the first question is the radiation levels low enough you could put a human on that part of the roof to patch it up? So Maxim, who I showed you in the photo, led his team and deployed a system which was based off the technology we've been developing. Very challenging conditions, 25-mile-an-hour winds, next to a structure which is predominantly steel, so huge magnetic interference. There's electronic warfare interference going on all of the time as well. So the fact that they were able to get data which could produce a radiation map across the arch surface allowed them to prove that it was suitably low enough over that area that had the hole that they put people on the roof to abseil down and fix it. So yeah, what was going to be a 100-year structure is no longer a 100-year structure, unfortunately.
Okay, we've got a question online. What is the nuclear sensor fixed on the drone? Is it a plastic scintillator or something else?
The sensor we use depends on the radiation levels. So when the radiation levels are really high, we tend to use a semiconductor detector. We use CZT as the material. That's either 5 by 5 by 5 millimeters or 10 by 10 by 10. And the reason we use that is a very fast readout. It's got very small volume of interaction, so it means we can operate at much higher doses. We can also use GM type detectors, so Geiger-Müller type, to go to the higher radiation levels. The only difference is when we use a spectrometer, we can pinpoint the radioisotope that's emitting the gamma. Whereas with a GM tube, you can just measure the intensity, but you don't know what it's attributable to, which is in some parts of the exclusion zone, you need to be able to differentiate the different emitters because they're quite varied and they don't all sit in the same place. For environmental stuff, we use cesium iodide, which is a scintillator type material and detector, and we use much bigger volumes. And it's those large volumes that we're starting to use now in terms of applying it to mineral prospecting and mining.
Okay, we've got another question online. David, you've got your hand raised. Just bear with us. We'll try and
Hello.
work.
Is this all right to ask the question, or would you rather I just type it and mute myself again?
Yeah, carry on.
Oh,
We can hear
All
you.
right. Have there been any sort of silver lining to the current state of the world? Is there is a lot of innovation in drones, unfortunately coming from drone warfare, but I know one specific in Ukraine is using a very thin, flexible fiber optic cable and essentially having the drone on a leash to avoid a lot of interference. Is any of that able to translate over to the work you guys are doing?
Oh, absolutely. So when I talked about shrinking the exclusion zone, if I was to try and do that with the technology that we were deploying in late 2021, it would be almost impossible because of the sort of jamming and electronic warfare capabilities that the Russians have put in place to disrupt the Ukrainians, and also vice versa. So the way I would do the exclusion zone mapping now would be with a fiber optically tethered drone. And that would be far more efficient in terms of these tethers can now go for as long as 20 kilometers, which is incredibly long. So there's an awful lot now in terms of advancement of drone technology. And when I talk about that, that's about increased flight time. It's more advanced control over long distances, and it also feeds into the battery technology, which also gives you that longer duration flight time or longer distance time, as you need to have the power to get you there. There are some bits of the development which are not applicable to us. So some of the technology development around batteries is around single cycle batteries. So batteries that you only ever charge and discharge once. That's not relevant to us. We want to fly our drones lots of times rather than just once. So yeah, very much if you think about how quickly drone technology has developed since 2021, it's in some aspects of the technology are almost unrecognizable over that period.
You get the red forest.
Yeah, we were looking at this. So in the center of the red forest, I wouldn't recommend camping out for the night. You're definitely into the millisieverts per hour, tens of millisieverts per hour range. So you'd accumulate your annual allowable dose very quickly. So very much when we were deploying over the red forest, we were not in the red forest. But there was one incident where we did lose a drone, thankfully not in the red forest, but to the south of the red forest, where we already had a risk assessment and an SOP for recovery of a drone. And the first thing is we had to make a judgment about whether the drone had gone down in an area we could access. So we had to establish that, had to have permissions of the Ukrainians that were with us. But then Yannick, Dave and myself, I think it was just the three of us. Oh, you weren't there. So it was Yannick, myself, Peter Martin. We put on all of our protective kit and wandered through a radioactive swamp to go and collect the robot. And what was amazing is the radiation mapping payload was still working absolutely fine. And I think we lost the tail off the vehicle. So that was it. So pretty light damage considering it eventually came down about 2 kilometers from where we were. Yeah, interesting times. Jamie.
Yeah, really fascinating talk. Thanks for that. Really enjoyed it. The nuclear industry can be a bit sort of reluctant to adopt new technology now and again. I wondered whether or not, like, to what extent has the industry now adopted the use of drones, either for like keeping them ready for the incident we hope won't happen, or for actually like routine operations, like knowing what's going on with their sites. Are they using drones on nuclear sites these days?
Yeah, so I didn't mention, but we were the first people to ever fly a drone on a nuclear site in the UK. And that led us to the work at Fukushima, actually. That was at Sellafield. And in order to get that flight completed, we had to develop a completely bespoke drone system. And we had to do, with Sellafield, we had to have a risk assessment to allow us to do it. Rolling on, that was 2012, 2013. Rolling on to today, drones are used on nuclear sites in the UK pretty much every day that's flyable. And that's for simple things like roof inspections, because it's much quicker to do it with the drone than to put up scaffolding. It's cheaper and faster, is to do routine monitoring. So we've had quite a lot of impact in terms of in that space. And you could also say with the quadruped dog robots as well, we deployed first at Chornobyl, and yeah, spots. Sellafield own plenty of spots. UKAA own something like 8 or 10 spots. The Ministry of Defence also uses them for radiation stuff, and other countries equally using them as well. So part of that is regulatory requirements to use the best available technology, which is good. But I think part of it is also, I think you'd be aware that at the moment the government is looking via a regulatory task force at how we encourage nuclear to be delivered still very safely, but in more effective, quicker, cheaper ways. And a lot of that is around using robots. So the regulator is very much looking at trying to support the use of modern technologies in ways that make a positive difference. So the government, to some extent, is helping us with that in the UK, and you'd say it's the same in the US and other countries.
Okay, we're running out of time, so thank you for all your questions. In recognition of Professor Scott's work in Ukraine, his colleagues at the National Academy of Sciences of Ukraine have honoured him with the Jubilee Commemorative Medal for the Institute for Nuclear Power Plant Safety Problems. So this is a great honour, and I'd like to invite Professor Jennifer McManus, Head of Physics, to say a few words and to award the medal.
Thank you very much, Tom. I'm very happy to be here. Evelyn Welch, the Vice Chancellor from the university, was going to award this medal. She has a daughter who's just returned from a US tour, so she couldn't be here today. So I'm going to say a few words instead. So I'm very happy to be here to present this award to Tom. He's a very distinguished scientist, and his expertise in nuclear materials and radiation has made a profound and lasting impact far beyond the laboratory. The Chernobyl disaster of April 1986 remains the world's worst nuclear accident, and he's just told us about the radiation and what he has done in doing that. And the release of radioactive material across Europe left a devastating and enduring impact on health, environment, and livelihoods of millions of people. And this highlights the importance of rigorous nuclear safety management. And we're very proud to be involved in that work in the School of Physics. Following the Chernobyl disaster, Tom and his expertise when going to Ukraine contributed vital work that has clearly helped communities and researchers build a better understanding and address the consequences of one of the most significant nuclear events in history. So it is in recognition of this exceptional contribution that Tom has been awarded the Jubilee Commemorative Medal of the Institute for Nuclear Plant Safety Problems of the National Academy of Sciences of Ukraine in honour of the 40th anniversary of the Chernobyl accident, awarded for his contribution to supporting Ukraine in the aftermath of the disaster. Please join me in congratulating Professor Tom Scott.
Well, oh, that's beautiful. Oh, so thank you very, very much. I must say, as I've said before, this is a team effort. It's the research team, because you don't do these things on your own for sure. And it's also the opportunity that was given to me by Ukrainian colleagues to let us there, to let us help. And as I said, this is part of the journey, and it's nice to be recognised partway through. But hopefully there's much more we can do. So thank you very much, everyone. Thank you, Jenny.